So before I dive headlong into the presentation, I would like to take a moment to acknowledge one of my colleagues, Dan Milam, for helping put together the presentation. In terms of the agenda, I'm going to give a little bit of background. I think some of those topics have already been covered. I'm going to talk a little bit about some of our learnings around project selection as well as benefits. And then I'm going to spend some considerable time talking about a specific example that we recently completed, a pretty large project in one of our chemical plants. And then I'll end with some concluding remarks. So as Mike has already been talking about, we believe that errors in executing procedures are a significant contributor in unplanned capacity loss. There's a number of publications and statistics that'll go and support that claim. Our belief is that automation provides a mechanism for ensuring consistency in terms of how your procedures are executed. It gives us the ability to address variations between how different operators would execute a procedure or even different shifts. And it allows us also an opportunity to standardize some response for common upsets that occur during your execution of procedures. When we talk to our sites, we tell them that the technology provides them with the opportunity to capture the knowledge of their most experienced operators. We like to think of it as this technology provides them with the ability to execute a procedure the way that your best operator would do it on his best day. And we also think that it provides the sites with the ability to perform some continuous improvement around how they execute their procedures. So when we talk about automated procedures at ExxonMobil, we're talking about two types of problems. First, we're talking about changes of state, so that might be grade transitions. It could also be blocked operation transitions, so we've got a piece of equipment that operates in different modes. We swing back and forth. We also develop a lot of safe park applications or rate reduction applications. The second type of problem that we attack is interactive procedures. So that might be cyclic processes, regeneration, decoke, catalyst switch, or basic startup and shutdown. So when we talk to people in ExxonMobil about the technology, we like to advertise that really the technology is well suited for handling a mix of field operator as well as console operator initiated actions. But we also provide the disclaimer that it's really not applicable to poorly defined or field-only procedures. So there are limitations in terms of when you'd want to apply the technology. It also provides a mechanism for standardizing and optimizing your performance procedure execution. But we find from time to time that we have to remind ourselves that it's really not a surrogate for a properly instrumented SIS system. We believe also it's a tool for improving operator effectiveness and reducing peak workload. So we like to think of this as this technology is operator initiated and it's interactive. So it's technology that's been developed to complement the operator and basically remove him from some of the minutia of executing complex procedures. So we're not really at this point talking about fully autonomous operations. And I also like to provide a reminder specifically internally in ExxonMobil that we're not talking about technology that's limited to batch or semi-continuous operations. We've done a lot of procedural automation projects on continuous units. So as Mike mentioned in the introduction, we've spent about 10 to 15 years developing a technology set for executing these types of projects. We've invested in an in-house shape library for the operator interface. So this is a simple test problem that we use in some of our training exercises. So you can see there are some blocks at the top where there's a little check mark. That's an indication that that's a step that's been completed. Then below you see a box with a cyan indication around it with basically white in the middle. That's a place for an operator to indicate that he's completed an action. He'll check that when he's done. There's a dialog box underneath that gives him an indication of what the sequence is waiting for. In this case, it's waiting for confirmation that a block valve has been opened. And we've got other different types of animations to indicate different statuses on steps that we're executing. We've also developed our own performance monitoring tools for Procedure execution, we've got an internal design and implementation guideline that we update regularly, and we have an operator and engineering training course that we offer. So we believe that a standard approach we provide a standard approach to programming sequences in the control system. We believe that a standard platform reduces the engineering effort to deploy these types of applications and simplifies the sustainment. The platform that we use utilizes function blocks as opposed to monolithic custom programming environments. And we have a number of reusable modules that sort of provide the backbone for the applications that we build. The platform is fairly portable. We can move things back and forth between sites, between our development system in Houston. In terms of project selection, I like to discuss the 6 different dimensions that we look at when we're evaluating a project. So the first thing we look at is the frequency of execution. One of the main barriers in our experience with getting operator acceptance around automated procedures is they have to have some experience that when they push the button, it's going to do what they want it to do. So that tends to favor procedures that execute more frequently as opposed to ones that execute on a yearly or semi-annual basis. The next 3 dimensions that we look at are basically things that I lump together, and they're really an indication of the complexity of the procedure that we're trying to execute. So the first thing we look at is the degree of interaction. Is that procedure primarily executed by the console operator, or is there a lot of action that goes on in the field? This tends to be why we back away from automated shutdowns. Is at a certain point you get to the point where a significant amount of things are going on in the field, and the operators tend to get annoyed by just continuously clicking a confirmation button that something has happened in the field. We also look at the number of steps. Laura gave a very nice example about things that have a few steps, you can lose your place. We tend to focus on procedures that involve a higher number of steps. We also look at what I refer to as the degree of distribution. We're looking at really the number of locations that an operator has to divide his attention. I mean, if you give them a procedure to execute and it's fairly linear and it's all sort of focused on the same place, they tend to do pretty well at executing those. But if they're having to take actions simultaneously on different parts of the unit, it can be a little bit more challenging. The other thing we look at is the consequence of error. These projects require the sites to commit resources, both operators as well as engineers, and we have to be competitive with other opportunities that exist in the plant for those resources. So we have to be able to demonstrate that we can provide a return. And consequence of error is a significant contributor to that. And I had some regret as I was going through this presentation that I put procedure documentation quality last, because that's actually the first thing that we look at. It's a real danger sign when we're handed a procedure that's been recently updated or hasn't really been accepted by all the different shifts. And we tend to, at that point, back away and tell the sites they need to go and work that a little bit more before we start trying to automate that. In terms of the incentives for automating procedures, one of the questions that I get a lot when I talk to people from other operating companies is, how do you demonstrate that there's any benefit to doing these types of things? I've divided that basically into 4 categories. I'm going to really focus on 3 because they're really illustrated by the example that I'm going to talk about next. But I would say margin improvement is a common thread throughout all of our applications. Basically every project that we work on, we have to be able to demonstrate some return. We're able to achieve margin improvement by optimized changeover time, reduced product downgrade or off-spec material generation, fewer trips or unplanned outages during the execution of a procedure, and increased service factor for our advanced control applications. In some types of problems, we see procedural automation as a real complement to our advanced control technology and a real enabler. The other category that we like to look at is abnormal situation management. So when we're executing a project, one of the things that we're doing is we're talking to the operators as we review the procedure. What are things that commonly go wrong when you're executing this procedure? These procedures the written procedures tend to be, at least the good ones, very prescriptive about telling you how to get from A to B. What they tend not to be very good at is telling you how to get from A to B when you get unexpectedly detoured through C. One of the other things that we'll do is, if we have the opportunity, we'll observe the operators executing the procedure and try to note some of the things that they're struggling with, or maybe not. We also can look at historical data just to get an idea in terms of what types of things the operator is doing outside of the written procedure as they're executing. One of the other advantages of automation is that we can incorporate feedback or adaptation. So the written procedure may say that you make a step change of 10 degrees in some reactor temperature, but you may have some other unit constraint that means that you can't really achieve that. So we're able to adjust our execution as dictated by whatever constraints we build into the application. I've talked a little bit about how we build multi-threaded applications. We're executing things that are happening simultaneously in a number of different places. We also believe that there's a reduced likelihood of a delayed response in a high workload situation. If what the operator has to do is push a button and the application takes care of a lot of things for him, it'll raise its hand when it needs something from him, and it gives him the opportunity to go focus his attention elsewhere. That's somewhat complementary to some of the workload reduction benefits that we see. We're able to redirect the operator's focus to higher value tasks. So rather than being consumed with the mechanics of executing a transition, he's really initiating and participating as required, and he's able to focus his attention at a higher level on basically optimizing the unit. We do see consistently a reduction in the number of process alarms for operations that have automated procedures, and we see improved shift handover. The graphics really become a mechanism to convey the process state. So this is an example from a chem plant at one of our large integrated chemical and refining sites. The information I'm presenting here I really like to think of as basically the case for action for implementing automated procedures at this site. We're talking about a single console with about 8 production lines, and I say approximately 8 because some of the equipment is shared and some of it can be redeployed based upon the mode that the plant's operating in. The important part here is that we're talking about an operation that's more than 2, but maybe less than 15 production lines. On average, each production line undergoes a grade transition every 2 to 3 days. There are simple grade transitions and there are complex grade transitions. On average, a grade transition takes about 8 hours. So simple grade transitions would be I'm transitioning from a material that's like to like on the product wheel. A complex one would be like to dissimilar on the product wheel. One other thing that's significant about these procedures taking approximately 8 hours is that this plant, they run 3 8-hour shifts. So if a procedure is started during a console operator shift, it's highly likely that he's going to have to hand over execution of that procedure to his relief. So this console rarely, in my mind, operates at steady state. The operator's attention is consumed by really the mechanics of performing grade transitions and responding to alarms. The planning group at this site tries to avoid having more than one product line in transition at a given time. So they've built some artificial operating constraints into the plant. And as I've described, conveying the state of the plant during shift handover is complicated. So there's a probability for error is increased, and there's considerable variation in terms of how grade transitions are executed. Now, one other thing I like to use to characterize this particular plant is that Within ExxonMobil, we have a methodology for evaluating how loaded a console is or how busy a console operator is. It's fairly extensive in terms of the measurements that we take. This particular console, before we implemented procedural automation, was squarely in the 4th quartile in terms of console operator loading. So this is a very busy console, very difficult to operate. So in terms of what one of these production lines look like, basically we have feed that comes in. It goes through a series of reactors. There's a separator unit afterwards, and then there's a stabilizer tower where we fractionate the product, and the product comes out the bottom. So what a grade transition looks like in a plant like this is, first we transition the unit feed to partial recirculation. So basically that's a lost opportunity as soon as we start doing that. We ramp to new operating conditions on the reactors and the separator. So that's feed, recycle, treat gas ratio, temperatures and pressures. We also transition the stabilizer tower to new pressure, as well as adjust the distillate draw and feed temperature. And there's also a step where we wait for confirmation that the product is on spec, waiting for lab samples. And that's a little bit more art than science, because typically the analyses that are performed take a bit of time. So if you pull your samples before the unit really is at steady state, if you have to do a retest, that's considerable time that you add on where you're operating the plant suboptimally. So aside from sort of the mechanics of executing this procedure, the operator is also responsible for monitoring some unit constraints. Could be operating temperatures, maybe delta T across the reactor, bed temperatures. And historically, this site observed that they had problems with level control when they were executing some of these grade transitions. So my guess is that these levels were tuned for disturbance rejection at steady state, and now they've introduced a large transient into the plant, and the tuning just isn't sufficient for that in that instance. So the way a project at ExxonMobil would be executed, we conducted a scoping study. It was concluded that grade transitions on 5 product lines would be automated. 3 lines were studied, but we really couldn't justify implementing automated procedures on that particular line, on those 3 lines. This project was a big project. It was executed in 2 phases. Each phase required about 1 work year of engineering effort. So that's design, development, and programming. The core team for the project consisted of 2 engineers from the central engineering organization, 1 site application engineer, and 1 operator. Both projects were executed using a similar milestones. That would be scoping, design, mid-project review, FAT, commissioning, and some reusable common components. Because we've got 5 lines, there are similarities in the grade transitions between the different lines. And at final step, before we closed out the project, we implemented some customized reporting on all 5 lines. So the first phase was completed in 2013, and the second phase came along about 2 years later in 2015. The service factors for this set of applications has been pretty strong on 4 of the lines. A 5th line has been a bit of a piñata for the operators. They like to, they've demonstrated that at times they can execute the grade transitions faster. Now, what's significant about that was that 5th line is the most simple of all 5 lines, and it had the most marginal benefits. But the site has been working with operations and really tuning up the application, and what you can see from the plot from the right is they've made a real difference in terms of the transition times for executing grade transitions. So over the course of about 18 months after they implemented all of the customized reports, they've been able to drive down their transition time by about 25%. Some of the additional benefits included considerably lower alarm counts. They now have scheduling flexibility that they didn't have before, and reduced errors due to handover. The site has continued with applications on 2 additional units, and they have plans for at least 2 additional projects after that. So in conclusion, we've learned over time that project identification and selection is critical. We made some missteps in the early days. There was a lot of enthusiasm for the technology. We didn't always select the right opportunities. One of the other difficult learnings that we've had over time is that we have to confirm that the systems can service the estimated data requests up front. So this comment particularly applies to some of our legacy DCS systems. The footprint for these applications doesn't look the same as a typical advanced control application. So we tend to be requesting data at a higher frequency on the order of 2 to 5 seconds. Our multivariable constraint control applications tend to be 15, 30, 60 seconds, and we tend to be requesting more attributes per point. So if you're not careful, you can make a bit of a mess in terms of the amount of traffic that you're requesting from a legacy piece of equipment. So initially, we did some work around consolidating data requests to avoid duplication, to try to make things more efficient. But within the last year, we've been doing a lot of work internally as well as with the vendor, and we feel like we're going to be able to make some good improvements over the next several months in terms of how much load we impose on some of our legacy systems. One of the other learnings is that it requires kind of an interesting skill set to lead these types of projects. You need somebody that has expertise with display development as well as sequence programming, but you also need somebody that has experience with operations, consensus building, and the ability to learn unfamiliar units. Our group currently in the central engineering organization is 4 people. So in one week, I might be working in a refinery. The next week, I might be in a polymer plant. The week after that, I might be in a chem plant. We're basically implementing projects all over the downstream, and we just don't have the luxury of developing specialists for certain operating areas. And one of the other things that's significant is, early on, our management decided that one of the skills that they'd like for people to have in this area is an understanding of advanced control. So we're really looking for people that understand the cause and effect of different actions that they take when they're executing a procedure and really understand the multivariable nature of our plants. So in terms of going forward, we need to be able to continue to deliver value, but we need to be able to do so with increased efficiency and lower sustainment effort. So a couple of areas where we need to make some improvements, we need to really be able to expand our ability to develop reusable modules. We have some that we've used. We need to be able to do more of that. We also need to develop a more flexible association between the sequence programs and the operator interfaces. These things are heavily cross-linked, and one of the concerns that our sites tend to have is they tend to be pretty proficient in terms of going in and modifying the sequence, but commonly they find that they're not as proficient with the graphics, and if they make a mistake, maybe the next time the procedure is executed, the operator goes to check a box and nothing happens. So we need to be able to provide something that's more flexible than what we currently have. And then one other area that we're interested in is better coordination with the field operator. In 2004, we had some work that we did where we were looking at mobile technologies, and we concluded at that point that it really wasn't ready for prime time in this area. But there's been a lot of development in this area, both in terms of wireless as well as cellular technology, and it's probably time for us to look at that again. So I'd like to thank everybody for staying here this late. And I've tried to share some of our learnings over time. We've been doing this for a little while, and I'd like to invite people to share their experiences either in the panel discussion or outside the session. So thanks.